The year 1640 witnessed the emergence of a seminal work in the history of mathematics, Pierre de Fermat's Methodus ad disquirendam maximam et minimam, a treatise that laid the groundwork for differential calculus decades prior to its more formalized development by Isaac Newton and Gottfried Wilhelm Leibniz. This method, far from a mere precursor, presented a fundamentally new approach to optimization problems, a realm that would profoundly influence scientific thought. To comprehend its significance fully, we begin by examining the intellectual landscape of early 17th century mathematics, the prevailing mathematical paradigm of the time, largely inherited from the Greeks, centered on geometry. While mathematicians possessed some tools for handling curves, the means of finding tangents, identifying extrema, and calculating areas under curves remained largely ad hoc and lacked a unified, systematic methodology. The burgeoning scientific revolution, spearheaded by figures such as Galileo Galilei, demanded a more precise and powerful mathematical toolkit. Problems involving motion, projectile trajectories, and the behavior of lenses all necessitated a calculus of some form. Prior to Fermat, mathematicians grappled with these challenges using methods that, while sometimes successful, were cumbersome and limited in scope. These approaches relied heavily on techniques of exhaustion, as seen in the works of Archimedes, a method based on approximating areas or volumes using increasingly smaller shapes, a process that was computationally intensive. Fermat's genius lay in his profound insight and his innovative use of algebraic techniques to tackle geometric problems. His method is centered on a simple yet elegant principle to find the maximum or minimum of a function. One considers the function's value at x and at x plus delta x. Here delta x represents an infinitesimal change in the variable x. Fermat then examined the difference between these two function values, divided it by delta x, and set the limit as delta x approaches 0 in the resulting expression. He then equated this to 0. This procedure, ultimately equivalent to finding where the derivative of the function equals 0, a core concept of differential calculus. To illustrate this, consider Fermat's method for finding the maximum of the function x squared minus x where is a constant. Fermat considered the function x plus delta x quantity squared minus and multiplied by the quantity x plus delta x, subtracted by x squared minus x. The difference between the two is divided by delta x. Setting the limit as delta x approaches 0 allows us to determine the value of x that gives the maximum or minimum value. The algebraic manipulation, a hallmark of Fermat's approach, yielded a simple equation from which the location of the extremum could be determined. This methodology offered a streamlined, algebraic procedure that bypassed the sometimes laborious geometric arguments of his predecessors. The immediate impact of Fermat's work was substantial. It provided a powerful tool for solving a range of optimization problems encountered in physics and geometry. Fermat himself applied his method to determine the optimal angles of incidence and reflection for light, a contribution that proved instrumental in the understanding of optics. His method found applications in determining the lengths of curves, calculating areas, and solving problems relating to the behavior of projectiles. He shared his results through correspondence with other prominent mathematicians of his time, including Marin Mersenne, René Descartes, and Blaise Pascal. These letters acted as a crucial means of disseminating his groundbreaking insights, providing the intellectual seed for the further development of calculus. Though a formalized calculus system had yet to exist, Fermat's method demonstrated a clear path forward. The legacy of Fermat's Methodus extends far beyond its immediate applications. His work profoundly influenced the subsequent development of calculus. Isaac Newton, in developing his own method of fluxions, a precursor to calculus, acknowledged Fermat's influence. Newton, in his Principia Mathematica, where he described his laws of motion and universal gravitation, relied on the principles that Fermat had pioneered. It is indeed likely that Newton's work was stimulated by the insights of Fermat. Leibniz, independently developing his version of calculus, also drew upon earlier works including Fermat's. The conceptual seeds of both Newton's and Leibniz's systems lie deep in Fermat's arguments concerning maxima, minima, and tangents. The reception of Fermat's method was initially mixed. Some mathematicians, accustomed to the geometric rigor of the Greek tradition, were initially skeptical of the algebraic shortcuts Fermat employed. Descartes, a formidable mathematician himself, expressed reservations about Fermat's methods, viewing them as lacking sufficient geometric foundation. This early criticism stemmed, in part, from the novel nature of Fermat's approach and its departure from established mathematical practices. The concept of infinitesimals, fundamental to Fermat's method, presented conceptual challenges, as did the lack of a rigorous justification for manipulating them. However, Fermat's supporters, like Mersenne, recognized the power and potential of his techniques. Further advancements refined Fermat's original method. The limitations were recognized and addressed particularly through the work of Newton and Leibniz. They provided the more rigid framework, including limits and derivatives, that addressed the issues of formal rigor. Newton provided the necessary mathematical rigor, and Leibniz provided the formalization of notation. The direct influence of Fermat's work extended through his communications with other mathematicians. Mersenn's network of correspondence served as a critical conduit for the dissemination of Fermat's ideas, fostering the exchange of mathematical knowledge in a time prior to widespread publication. The correspondence between Fermat and Descartes, although at times contentious, provided a forum for debate and clarification. Fermat's Methodus ad disquirendam maximam et minimam stands as a watershed moment in the history of mathematics. It offered a novel approach to solving optimization problems. It provided a powerful algebraic framework that would reshape the landscape of mathematical inquiry. It profoundly influenced the development of calculus, providing a critical step towards the scientific revolution. Although it did not achieve the complete, formal system of calculus that would arrive later, it laid a solid foundation in the most impactful areas of science and mathematics. His method allowed for the solving of physical problems and allowed the field to move forward. Its impact can be seen today.